Hello, everyone. Thanks for attending this session. The topic is the next generation of bucketing. Improve Spark SQL performance by removing shuffle. I'm Guojun, and my English name is Jason. I'm the lead of data engine team at Bytedance. Let me introduce who we are and what we do. We are data engine team of Bytedance. We build a platform of one-stop experience for OLAP, on which users can build a EB-level data warehouse and analyze TB-level data by writing SQLs without caring about the underlying execution engines. We offer an open API and a self-serve platform. Besides, we optimize Spark SQL, Presto, and Hive data engines. And at the same time, we design data architecture for many business lines in Bytedance. My presentation will consist of 4 parts. The first one is Spark SQL at Bytedance. Next one is what is bucketing. Then I will introduce Spark bucketing limitations. And the last, I will illustrate what we do to optimize Spark bucketing. Let's go to the first part, how Spark SQL works at Bytedance. We introduced Spark into Bytedance at 2015. Before 2016, Spark SQL, we just run Spark SQL for a small-scale experiments. And at the end of 2017, Spark SQL support parts of ad hoc queries workloads in Bytedance. Then at the end of 2018, Spark SQL support most of ad hoc queries and few ETL pipelines in production. At the end of 2019, Spark SQL support a majority of ad hoc queries and most of ETL pipelines in production. Now, Spark SQL is the main engine in data warehouse area at Bytedance. Let me briefly introduce what is bucketing. Now, first we should create a bucketed table into 2 ways in Spark SQL. On the left side, we can create a bucket table in the Spark way. Create a table order using Parquet, clustered by user ID, sorted by user ID, and into 1024 buckets. In this example, we can say that we need to specify a user. We need to specify the bucketing key set with clustered by clause, and we also need to specify the sorted by key set with sorted by clause. And what we need to know is that the sorted by cases could be different from the clustered by cases. And on the right side, we can create a Hive compatible bucketed table. Create a table order clustered by user ID and sorted by user ID into 1024 buckets stored as Parquet. It's stored as Parquet, not using Parquet. So with this method, we create a table which is compatible with Hive engine. When we get a bucketed table, we can insert some data set into the bucketed table, like this. Insert into order. Select order ID, user ID, product, amount from order staging. We can see that we just insert some data into the bucketed table, like what we do to insert the data into a non-bucketed table. In another word, when user insert some data set to the bucketed table, she do not need to know whether this table is bucketed or not. When we get a bucketed table and populate the table, how we can benefit from the bucketing? Let's take a shuffled hash join as an example. We know shuffled hash join is one of the popular used shuffle mechanism in Spark SQL. When shuffled hash table is selected, we need Spark SQL need to ensure that both tables are co-partitioned. That is to say, if we want to join the order table and the user table on user ID, Spark SQL need to ensure that both of them are co-partitioned on user ID. if they are not co-partitioned, Spark SQL will add some shuffle. In Spark SQL, we use the exchange operator for shuffle. So in this picture, we can see two exchange nodes. Both of them are on user ID, so that after the exchange, both of them are co-partitioned on user ID, so that shuffle hash join can be used. But if both of them are bucket table, that means that we set the table to bucket table before we populate them. Then we do not need to add some exchange nodes before the join, because both of them are pre-shuffled on user ID. That's why we want to use a bucket table. Let's go to the sort merge join. Sort merge join is another commonly used join mechanism. For sort merge join requires that the child plan should be co-partitioned, and also they should be sorted on the join key set. For example, if we want to join the order and the user on user ID, the Spark SQL will ensure that both of them are co-partitioned on user ID, and each partition is sorted on with user ID. Otherwise, Spark SQL will add exchange operator and sort operator to ensure this. But if both of them are bucket table and also sorted on user ID before we populate the table, then we do not need to add the exchange and sort node again, because both of them are pre-shuffled and pre-sorted. That's why we want to set the table into bucket table. Let me introduce what's the limitations of current Spark SQL bucketing mechanism. One of the most important limitations is small files. Let me take the below SQL as an example. We can populate the table with insert into order, select order ID, user ID, product amount from auto staging. When the SQL is running, we take a snapshot on how many files are there in a single task folder. We count this by HDFS, DFS, LS, and then we count the files, and we found that there is 988 files under a single task folder. Each task will generate up to 1,024 small files. The 1,024 is the bucket number. Just remember that we created the order table with 1,024 bucket number. And there will be up to 1,024 multiply m small files in total. M is the task number. When m is 1,024, there will be up to 1 million small files. And in practice, m may be much larger than 1,024. For example, 10,000. Then there will be up to 10 million small files. We know that for Hadoop ecosystem, small files may incur some disaster, because when there are too many small files, the Spark SQL need to communicate with the HDFS name node frequently, and the HDFS name node is single point. Will be the bottleneck. So when we do it like this way, the SQL will run very slowly. Okay. Even when we finish the data populating, the downstream SQLs will also run very slow, because they need to open too many small files, and which is very slow. So I think this should be one of the most biggest limitations. Also, we can use some other mechanism to solve this problem. For example, we can add the distribute by clause, and also we need to set up the Spark SQL shuffle partition configurations to some value. There are up to 1,024 files when 1024 is multiple of m. And there will be up to m files when m is multiple of 1024. Otherwise, there will still be up to 1024 multiply m small files. M equals to the value of Spark SQL shuffle partitions. Yes, we can reduce the file counts by this configuration and the distributed by clause, but it's difficult for end users to set the configuration. So we need a mechanism to reduce the files automatically. The next limitation is that Spark SQL bucketing is incompatible across SQL engines. For example, Spark SQL bucketing is different from Hive bucketing, and also Spark bucketing is different from Presto bucketing. Presto and Hive bucketing are compatible. There are two reasons why they are incompatible. Firstly, when Hive writes the data into Hive bucket table, an extra shuffle will be introduced to ensure that each reduced task will write exactly one bucket file. But for Spark SQL, there will be no extra shuffle. So each task will write into up to n bucket files, each of which will be very small. Secondly, they use different hash mechanism. For Hive will use Hive hash, but for Spark, memory 3 will be used. So the data distribution will be very different. That's why they are not compatible. Because they are not compatible, so exchange and sort are required when joining tables with Hive bucketing in Spark SQL, or joining tables with Spark bucketing in Hive. In 2019, we migrated tens of thousands of Hive SQLs to Spark SQL, but many of them use bucketed table. So we have to make them compatible so that we can migrate the SQLs automatically. Besides, in Spark SQL, extra sort are needed. Since the bucket in Spark SQL will consist of more than one files, so Spark have to sort the files within a single bucket to ensure that the whole bucket is sorted on the join key, so that sort merge join can be used. Another limitation is that Spark SQL requires that if user want to join two tables, and if they want to use bucketing join, both of them should be clustered on the same key, and the bucket number should be the same. For example, if the order table have 4096 buckets on the left side, and the user table have 1024 buckets on the right side, then Spark will exchange the user table into 4096 buckets so that it can be joined with the order table. So in this picture, we can say that even though both of them are bucketed table, but exchange is introduced because they have different bucket number. Another limitation is that Spark SQL requires both of the table are bucketed on the same key set as the join key set. For example, if both table are bucketed on a user ID, but we want to join them on user ID and location ID, then exchange will introduce for both of them. The next one is that when we use the union or clause, exchange will be needed. For example, maybe the order will come from both web and mobile, and we want to union the order web and the order mobile, and then join them with user ID. In this example, exchange will be introduced because after union, the output partitioning and the output ordering will be set to unknown, Spark SQL cannot know that the underlying tables are bucket table, so the exchange will be introduced. Let me introduce how we optimize bucketing at Bytedance. Firstly, we align Spark bucketing with Hive. When previously I introduced that the two difference is that the file number is different. For Hive, there will be exactly one file for each bucket, but for Spark, there will be more than one files for each bucket. So we need to ensure that in Spark, each bucket will consist of exactly one file. And another thing we need to know is that Spark use murmur3 hash and Hive use Hive hash. So we change Spark SQL to use Hive hash when bucketing when we read or write bucket table. The first, so we need to do the below things to ensure that Spark will write the data to Hive bucket table in the same way as Hive. Firstly, we change the required distribution of insert into Hive table plan, and we set the value into hash cluster distribution with Hive hash on bucketing case, and also we overwrite the required ordering into sort order on bucketing case with ascending. In this way, we ensure that the table an additional shuffle will be introduced to ensure that each task will write only one bucket table, and the task number will be the same with the bucket number, so that there will be exactly a bucket file, and each of them are for a single bucket. So when Spark so Hive can read this data as in the same way as Hive. The next step is that we need to Spark need to recognize the Hive bucket table. So we override the output partitioning of Hive table scan exec into hash partitioning with Hive hash on bucketing case, and then we override the output ordering into sort order on bucketing case with ascending. Let me illustrate more with this picture. On the left side, we say that without our changes, the output partitioning of Hive table scan is unknown partitioning, and the output ordering is nil. That's why Spark still need to add the exchange and sort node for sort merge join, even though they are Hive bucket table, because the required child distribution for the sort merge join is hash clustered distribution, and the required child ordering is sort order, and the output partitioning for the Hive table scan is unknown partitioning, which does not satisfy the required child distribution of sort merge join. Okay, after the change, we set the output partitioning into hash partitioning on the right side, and which can satisfy the required child distribution of sort merge join, which is hash cluster distribution. And also the output partitioning of Hive table scan is changed to sort order, which can satisfy the required child ordering of sort merge join, which is sort order. So exchange and sort are not needed anymore. In this way, Spark SQL can read the data from Hive bucket table, and Spark SQL can join two of them without shuffle and sort. Now the Spark SQL and the Hive bucket table are compatible. The next thing we do is that we support the one-to-many bucket join. Let us take this as an example. For table A, we say that there are three buckets, and for table B, there are 6 buckets. For Spark, if we join them in Spark, the extra exchange will be needed because they have different buckets. But in our company, we need to support this case without exchange. The first method is that we can combine bucket 0 and bucket 3 in table B, and combine bucket 1 and bucket 4 of table B, and combine bucket 2 and bucket 5 in table B, so that after the combination, the table B will have 3 buckets, so that they can join with table A without shuffle. On the right side, we can see that we can combine them with sort exec. So the physical plan will be like this. We scan the table B and sort the table B. Then it can be joined with table A without shuffle. Besides, we provide another mechanism to support the one-to-many bucket join. Because the previous methods have some limitations, the parallelism will be 3, which may be too small. And we provide another mechanism, say, so that we can use 6 as the parallelism, and there will be 6 tasks which will do the bucket join. But how can we do that? We can clone the table A, so that table A will have 6 buckets, and and we clone them by a new mechanism named bucket uni. We know that Spark supports a mechanism named uni, but if we simply use the uni, the uni operator, the output partitioning will be unknown. So we provide another new physical plan named bucket uni, so that the output partitioning and the output ordering were kept. So after the bucket uni, it can be joined with table B without shuffle and sort. Yeah, even though we remove the shuffle and the sort, there are some other problems. For example, this mechanism works well if B left join A and B left semi join A, or B anti join A, or B inner join A. But if we join the B and A with B right join A, or B full out join A, or B cross join A, there will be some duplicated records because we just scan the table A twice, right? We dynamically add a filter to resolve these problems. For example, the filter will be like this: the hash the join ID and then mod the number of buckets, and we need to ensure that the result is the same with the bucket ID. Let's take the bucket 0 as an example. There are 6 records: 0, 3, 6, 9, 12, and 15 for bucket 0. But what we need is 0, 6, and 12. So we hash the ID and then mod with 6. And for 3, 9, and 15, which is not the targeted numbers, and when we mod them with bucket with 6, the result will be 3, which is different from the bucket ID 0. Then 3, 9, and 15 will be filtered out. With this mechanism, there will be no duplicated records anymore. The next thing we support is that we support joining on more than the bucketing case. On the left side, we can say that the table X is bucketed on A. A is the column name. And on the right side, the table Y is bucketed by A, and A is also the bucket column, the column name. But the SQL query requires that we need to join table X and table Y on both A and B. So exchange and sort are introduced. Exchange on A and B, and sort on A and B. Okay, this limitation requires the users design the table bucketing very carefully, and sometimes it's not very easy for users to pick up the best bucketing mechanism. For example, if the frequent queries are like below, select from table 1 group by A, B, and C and D, and select from table 2 group by B, C, D, and select from table 3 group by B, D, E, and sometimes users may want to join table 1 and 2 on AB, or and join 2 and table 3 on BC, and join table 1 with table 3 on BD. How can we set up the bucketing case? If we bucket table 1 with A, B, C, and D, so we cannot use bucket join when we join table 1 with table 2. To resolve these problems, we support a mechanism which support joining on more than bucketing case. Let's go back to the example. The table X is bucketed on A, and the table Y is bucketed on B. In this way, we do not need to introduce exchange, and what we need to do is that we can sort on A and B for table X and table Y. Then we can join table X and Y with sorted join and without exchanging nodes. By this way, we can design the bucketing key sets very easily. Let's go back to the previous page. In this example, we can say that we can just set column B as the bucket mechanism. So because the B is the bucketing key set, so all of these queries can benefit from the bucketing mechanism. For when we join table 1 and table 2, we can use bucket join because B is the bucket key set, and the join key set is the superset of B. And also, we can join table 2 and table 3 with bucket join because the join key set is B and C, which is the superset of bucket key set. The last one is that we support bucketing evolution. Let's take these two cases as an example. Case 1, a non-bucketed table is partitioned by date, and the user wants to convert it to a bucketed table without overhead. By default, if we want to change the non-bucketed table as a bucketed table, we either to convert the existing data into the bucketed distribution, or when we query the existing data, the query will fail because the existing data is not bucketed yet. And case 2 is that the bucket number may be X, and the user need to enlarge it to 2 multiple X because the data volume increased. To resolve these problems, we provide a mechanism named bucketing evolution. To achieve this, we put the bucketing information into partition parameter. We know that in Spark SQL, the bucketing information is in the table property, not in the partition parameters. And by putting the bucketing information into the partition parameters, we can know the bucket information for each of the partitions. And only if all target partitions have the same bucketing information, will the table be read as bucketed table. Otherwise, it will be read as non-bucketed table. For example, the table is non-bucketed, and today we converted it into bucketed table, and the partition for today's data will be distributed by and sorted by the bucket key set. Tomorrow, when we query on this table, and if the only targeted partition is today, then Spark will know that it's a bucket table, and the bucket join can be used. But if the query need to read data for both today and yesterday's data, Spark found that the targeted partition have different bucketing information. So Spark will read this table as a non-bucket table. And reading a bucket table as non-bucket table only impacts the performance, but not the correctness. So it works well in our practice. Okay, this is all for my presentation. Thanks